All right. I suspect we're going to have a few more stragglers join us as other programs end, but I want to be respectful of the people who joined us on time. So we're going to get going, everybody. So thank you for being here with our session today with SimuTech. I'm going to let our hosts introduce themselves properly in just 1 second. So I'm Ken Rother. I'm the director of Ithaca Startup Works, which is a incubator in downtown Ithaca. It's part of the Cornell system of incubators. Um, we're domain agnostic, but we have a number of programs that are specifically focused on hardware. So people building stuff that is physical in nature. It might have software in it, it might have electronics, liquids, whatever, but it's, they're atoms, not just bits. So we're beyond service and beyond SaaS and applications and so forth. So one of our newest sponsors actually are the folks from SimuTech, and they help companies kind of make sure they're building the right thing, that what they're building is going to work. And we're thrilled to have them with us today, and we're thrilled to have them as a sponsor. So I'm going to pass it on to Jordan Grills to sort of lead this session, and he has a number of folks from his company who are helping. They each are domain experts in various topics. If you have a question, there's a Q&A platform at the bottom. Type in your question, and we will try and get to it as we go through this session. But if you have a question, please put it in the Q&A platform. So without further delay, Jordan, let me pass it to you.
Awesome. Thank you so much, Ken. So yes, I appreciate firstly you having us on here to discuss this content. Been down to Rev Ithaca a couple of times now, and I think I speak from everyone at SimuTech. We're absolutely thrilled to be a partner of yours and a sponsor for the group. I think the alignment is obviously there, and really what the point of this conversation today is to discuss what simulation first of all is, the physics involved in it, and then obviously we have other subject expertise on the call to handle those specific physics. But what does that look like for you as a startup, as a company just beginning? That's what we're going to mostly dive into today. And obviously, as Ken said, we do have some time left at the end for questions. So please feel free to fill up that chat box with any kind of questions you have as we go along. I'll start off with an introduction of myself. So I'm an account representative with SimuTech Group. I am based out of the headquarters of SimuTech in Rochester, New York. And I really handle the, kind of like that middle person between the small business and Ansys. So we'll get a little bit into the simulation, what kind of Ansys is, what the tools are as we go along. But my role primarily is to work with small to medium-sized businesses to evaluate what they need. And obviously, if there's cases where the software just doesn't make sense, we'll get into some of the other options we have in concerns of consulting and training and stuff. But really open to any kind of questions you guys have. Don't be shy. On that note, I don't know if we want to have our engineers just do a quick introduction of themselves, and then we'll get rolling with the rest. Sound good? Okay.
Sounds
Yeah.
We'll start with Tarek.
Yeah, my name's Tarek. I'm one of the electromagnetic engineers here. I mostly deal with low frequency, and I'm based out of Michigan. Thank you.
And I'm listed next. So I'm Lauren. I'm an optical engineer with SimuTech. So I deal with things that are related to light. We'll talk more about what optics means later. And I'm in New York City.
I'm Ben. I'm primarily a structural engineer, and so deal with anything structural. I'm in Chicago.
Great. Thank you, three, for sharing. Gabby, would you go to the next slide, please? All right. So again, to run through what we'll be talking about, honestly, my portion of it is more of the logistics or the introductions part of it. So I promise I'll keep this short so we can get to the fun stuff. But we'll cover who is SimuTech Group, what is simulation. We'll get into actual overviews of the three physics that our engineers who are joining us today specialize in. And then towards the end, before some questions, I'll just do a quick overview of what the Ansys Startup Program is. All right, so SimuTech Group is the largest Ansys partner in North America. So as a channel partner, which we are actually an Apex channel partner, We essentially are, in some ways, some people can consider it a reseller, but in more ways than just selling the software, our team supports beyond just the software side of things. So in the Ansys world, and I will just say this too as well, if you guys are up to date on the news, Ansys was just acquired by Synopsys. So we are now Ansys powered by Synopsys, but either way, SimuTech Group stays the same as the channel partner for all of North America, which also includes Canada, which is where I am today, actually, in that Montreal office, which I'm sure people are good at a map. That is not anywhere near where Montreal really is, but we ran out of space. So 4 main offices, the Rochester, New York headquarters, Toronto office, Seattle office, got about 150 plus employees. And among those 150 plus employees, I'd say at least 60 to 70 of them are engineers. And we're constantly growing. You know, as our account base grows, as the size of the accounts that we support and the companies continue to move along their simulation journey, get bigger, we, as a result, need more and more engineers to help support these clients. And amongst all of those engineers that we have across the company, it does add up to about 900 plus years of experience. Again, a lot of the engineers that we have come into our company with previous Ansys experience, continuing to learn more as the simulation software evolves and changes over time through updates. We continuously, improve upon our own internal training as well as side-by-side trainings with Ansys.
Cool.
All right, I will breeze through this slide, I promise. So first, well, I guess I gotta go to the top there. There we go. So we do, outside of, I mentioned selling the actual software licensing, we do offer consulting as a part of our services group. So essentially that's, hey, I don't have the time, the resources, or the capital to invest in the software itself. You'd reach out to us, you'd have a conversation with one of our engineers, we kind of put together a scope of work. And then from there, we provide you with pricing for what we believe would be a sufficient amount to be able to do the work for you. This is a good, obviously, for something that maybe if you had invested in the software, if you have other tools, you want to try it out or have us kind of prove out what you're going to be designing first. Outside of that, we do offer training. That would be on-site training, either in our headquarters or on-site at a company location, which would be considered a private training. And we also offer one-on-one mentoring, which I like to consider to keep it collegiate for you, like office hours. Bring us your problem and let the professor do it. I mean, help you with it, right? That's what it is. That's what our mentoring is. Outside of all that, you do get the dedicated support. All of our clients do also, I don't believe there's a slide list, but they do have access to the SimuTech Skills Center. So that gives you tons of videos, webinars, tips and tricks, various levels of trainings that you can go and kind of work at your own pace to complete. All of that to kind of enable you and our users to feel comfortable with using the software, as I think our engineers could say themselves when they go, isn't necessarily easy. Where's, I think, oh, there we go. What is simulation? So I'll do this quick. This is not the Webster Dictionary version of what is simulation, but I believe it kind of gives you the best gist of what it really is. So essentially why people would use simulation is they need to test out these, real world scenarios while not having to invest a ton of money into making prototypes. Obviously, physical testing, and especially in some fields like electromagnetics, to get compliance or to be, certified, you have to do some type of physical testing. But even those testing are also very expensive. And if you fail, you fail. You have to do it over again. What simulation does is kind of steps into in the forefront of that process, in between kind of the idea, the design stage, through all the way to the prototyping phase. So essentially what this is doing is it's going to either speed up the process that you can get to a product that actually works, or it could, on occasion, even eliminate the need for costly physical testing. And just to kind of get an idea of, what type of companies this typically works with: aerospace and defense, medical devices. I would say energy, green energy is a huge, obviously booming industry that's continuing to grow, as well as into healthcare, automotive. I mean, there's tons of solvers just completely dedicated to the automotive industry too as well. But on top of those industries, I'll just cover before we hop into the fun stuff, the physics types. Today, we will be covering electromagnetics, optics, and finite element analysis or structural analysis. I will say this, although we don't have anyone talking on computational fluids or CFD, we have phenomenal resources and engineers here at SimuTech that if you do have interest in that particular physics or that solver, reach out to me, shoot your email or contact information into the chat, and we'll set up a time to have you talk directly with one of our engineers on that. I'll get off my soapbox. You're up, Tarek.
All right, so my name is Tarek. I'm one of the engineers, like I mentioned, for the electromagnetics. I mainly work on the low frequency. I'll be talking about low frequency and high frequency. So, Gabby, do you mind going to the next slide, please? So this shows like the general software that we have across the different physics. And if you click next, I'm just going to highlight the electromagnetic. So we have a few different softwares. In fact, we have more than these, but these are the popular ones. So if you have any applications or any questions about something that maybe we didn't touch on, feel free to let us know. There's probably something there for you. Click next. So like I mentioned, low frequency, but I'll be talking about both. We have different software: HFSS, Maxwell, SI Wave, IcePack, Q3D, MotorCAD, Sherlock, and EMA Cable. Sherlock and EMA Cable, we're not going to be talking about now. They're a little bit more on the niche side, but the people who use them really benefit from them. So next slide, please. So HFSS is the flagship high frequency solver. And what we mean by high frequency, it's a bit of a sort of, depending on the application, the size will not, but think about in the megahertz, upper megahertz, gigahertz range, things like antenna, filters and stuff like that. It is the gold standard. It's the most popular, widely used. It's an industry standard, and it is a full 3D solver. And HFSS stands for High Frequency Structure Simulator. And it is generally used for PCBs and filters and whatnot. We'll talk about the applications. So if you don't mind going to the next slide, please. Here's some of the main applications that would use HFSS, and it's not limited to these, but some of the more popular ones. Antennas, 5G, RF, NFC, stuff like that. Anything with data transfer like that. PCBs, boards. Here we have like a USB board. You're looking at the data transfer and some of the designs. There's EMI, EMC, which is a very popular one nowadays. That's electromagnetic interference or electromagnetic compatibility. I know testing for those can be very expensive, and if it fails, you have to go back and redesign your product. So simulation helps you get a better design from the beginning. Biomedical applications, you get human tissue, like the brain, you see the image there. You could put like sensors and stuff like that. Automotive radars and filters and connectors and other things. Do you mind going next slide, please? Here's some examples of the simulations. Because of the wide breadth, we just show some examples. The first one shows you signal integrity and power integrity. One of the nice things about simulation is it allows you insight into things that are hard to test. So in this case, you could you could see some odd behavior in your application. You want to look at a specific frequency or electric field. It's sort of difficult to visualize electric field experimentally. So you could hear in the simulation, narrow in on your application, see if you have hotspots, anything like that, for specific frequencies, if you have any resonances. The next one shows like autonomy. So if you want to look at cars, there's something called SBR type of simulations used for that. The one at the bottom left is called co-site simulation. So sometimes you have to put a bunch of antennas, a number of them in a plane, and you want to look at placement, make sure that they don't interfere, they have good coverage. Same thing with this smartphone biocompatibility. Yeah, you may design a good antenna, but how does it work when you have human sort of fingers touching it, changing the impedance and whatnot? And then we have filters. You could do high pass filters, low pass, band pass, and then antenna placements. What is the best placement for antenna in your car or in your any type of vehicle or any application? Next slide, please. This is the next software. It's Ansys Maxwell. This is the one that I use quite frequently. And this is the low frequency equivalent. And it is 2D and 3D. It uses the finite element method in the background. And The frequency, when you say low frequency, it's think of it as DC, maybe in the low megahertz, depending on the application. But it's popular, anything line frequency in the hundreds of kilohertz, we'd use it here. And it is very popular and is the gold standard. And here's some applications with rotors, linear machines, actuators, and transformers. Next slide, please. So some of the main applications, again, not limited to these, things like sensors, hall sensors. You could have things like actuators, solenoids, motors, anything with magnets, magnetic latching. Sometimes you want to move magnets and induce current into conductors, wireless charging, like you see with your phones or your cars, wireless heat transfer, anything like that. Induction heating is a popular application, and then arc modeling and anything with static magnetics. Next slide, please. Here's some examples of the simulations. We have power electronics. Sometimes you want to look at inverters and components like that. We mentioned wireless charging. That is a pretty popular application for it. And wireless charging could be for phones, could be for very small components. It could be also with the medical applications, like MRI. MRI has it's a magnetic resonance imaging, so you want to simulate the magnetic field. You could look at that in Maxwell induction heating. But one of the most popular applications is electric machines, so motors, generators, and stuff like that. And one thing, go back, HFSS and Maxwell, they live in the software called Electronics Desktop. They use the same graphical user interface, so learning one or the other makes it a bit easier. Just some nuances with the physics are different. Next slide, please. One of the popular newer Ansys software is called Ansys MotorCAD. This is a software that lives outside of the electronics desktop, but this software is essentially specific for motors and generators, and it's a template based and has some finite element components, but it's so specific for motors. So motor designs and experts are very benefit greatly from it, and it has a lot of expertise behind it. So the people making it are motor experts. If you go on the next slide. It's used for different types of motors, and these are the examples here. You could read them. They just added axial flux motors, and it has a lot of templates and parameters. So one of the nice things about it is you could just change the parameter number. So you could say, how would my motor, look like with 24 poles versus 36 poles. So you may want to optimize for weight, torque, force, some of the other things. It's easy to change numbers and it's very fast. Next slide. It has different modules. We just go quickly through them. There's an electromagnetic module. This is it's an 2D FEA solver. You could look at different winding parameters, how you connect the windings, the number of turns, all this kind of stuff. You could look flux density plots, like you see in those images. Do you have any hotspots or any sort of saturation effects? And then you could look at the waveforms, torque, forces, voltage, current, power, and stuff like that. The next module is the thermal module, and this is a very powerful module. You could look at steady state or transient temperatures. You have a thermal network, and you could also do some type of feedback where you could then operate the motor and feed the temperature back and obviously affect some of your properties. And it's very fast and it's pretty useful. The next one is the lab. This is if you want to do efficiency and loss maps and torque speed curves. And then the mechanical one, it's FEA solution based. So if you want to look at stresses in the motor, vibrations and whatnot. And one last thing is that you could sort of design this very quickly and then export it into a Maxwell problem and solve the full 3D FEA simulation. Next slide. Uh, we have Ansys SI Wave. This is a 2D, 2.5D solver. It's a hybrid solver, full wave. It's run on ECAD. It's usually used for printed circuit boards. You have large boards. You could also couple it with HFSS to create submodels. If you want to look at signal integrity and power integrity and EMI and EMC. This is really good for insertion loss and S parameters. And it's very specific, highly specific, but people who use it definitely benefit from it. Next slide. Q3D is one of maybe the lesser popular ones, but it is a field simulation for parasitic extraction. So if you want to get conductance, inductance, capacitance, resistance, stuff like that for your circuits, then that's what you would get. Next slide. This is the last one that we're going to talk about today, but this is IcePack. This is a thermal solver and flow solver. So if you want to look at your applications, you want to simulate the heat flow or the airflow, so you have fans, cooling fans, anything like that, you could include it here, and it couples with Maxwell and with with the HFSS, or you could actually include your own heat generation sources, and you could sort of move things around, see how the temperatures look at it, and you could also do feedback. So you could sort of feed the temperature back to Maxwell and do some type of thermal feedback to make sure the temperatures are safe. If you look next, you can see the next slides. These are just examples of some simulations. So if you have heatsink fans, PCB maps, you could have sort of airflow into your, let's say, your electronic components. You could have in this case, like a projector or anything where you could want to look at flow, you could look at temperature only. Technically, this uses Fluent, which is our CFD solver in the background. You wouldn't know about that, but that's it. And this lives in the electronics desktop interface. Thank you very much.
All right, so now we'll be talking about optics. So like I mentioned before, optics is anything that has to do with light. It's not just your eye. So I kind of like to think about optics as falling into three main categories. The first being imaging optics, and this is like the vast majority of optical systems that we typically simulate just because of the performance that's required. But any system that forms an image, whether it's a microscope, a telescope, a camera, your cell phone, those all require lenses like glass or plastic components to get an image from the scene and put it either like onto a sensor or to be viewed by your eye. And your eye is another example of an imaging system. Next category is illumination optics. So any type of system where you're trying to get light from a light source into a target area. So you can think of like a flashlight, headlights on a car, or even your computer screen is you wanted to have it be illuminated uniformly. Those are kind of illumination optics and also things that we can model in software. And then the third category is laser optics. So laser light's a little bit different from like light sunlight or like a flashlight in that it's coherent, which basically means that it can like store information. So when we talk about fiber optics, communications, sending information to a satellite and back, or like LiDAR systems, those all are using lasers because they're able to encode information, and we can also simulate those. And kind of all three tools have capabilities to simulate all of them, but they each have their different strengths. So I'll talk about so the Ansys optics portfolio is made up of three different tools: numerical, Zemax, and Speos. And like at the core, it's basically just what size you're working at, like what the feature size you're working with. So on the smallest scale, nanoscale, you have numerical, which is our photonic design and optimization tool. So if you're trying to design any photonic components, circuits, or systems, this would be the tool for that. It's modeling light as a wave, so you're able to take into account interference diffraction, and as such, great for designing diffractive optical elements, which requires super tiny structures, as well as waveguides, and then also any emissive and absorbing structures. So like, the generation of the light itself in an LED, or how the light is absorbed by a sensor. Going up in scale, we have Zemax. This is the one I use the most. This Zemax Optics Studio is our optical design and modeling tool. So this is like typically more handheld size components. So this is where we'd actually, design the lenses that go into a camera, as well as the mechanics that immediately surround it, and just look at the performance of the optics under various conditions, and different tolerancing, how it was built. That's what Zemax is primarily used for. And then we have Ansys Speos, which is our full optical system modeling tool. So now it's like we're taking our optics into the real world. We want to look at how a scene will look when it's like a sunny day out or a cloudy day out, and there's different street lights. We have different material properties. How does it all play together into creating a cohesive image? And so this is like a 3D CAD type environment, where the others are less so like that. And it also has ability for human vision rendering. So anytime you're designing a product that's going to be shown to a customer. It's a really good way to like validate that, you know, I'm designing a iPhone screen and I want to make sure it looks bright and it's readable even on a sunny day. How bright does that screen need to be so it's legible even on a sunny day? You would need something like Spios for that. Next slide, please. So another way that we can talk about is like how all three of these tools could come together for a single like product design workflow. So something really great about Ansys is that all of the different tools, all the different softwares play really well together. There's a lot of connection points between them, whether it's like, in this case, it's, you know, all the same physics, it's all optics, but it's of different scales. So we can do different multi-scale simulations, and we can also do different multi-physics simulations, which I'll talk a little bit more about later. But, you know, we have our three separate engineers presenting on electronics, optics, and like structures, but all three of those areas talk to each other, can pass information back and forth, and really give you a full picture, a full like digital twin, it's called, of what you're trying to build. So, for example, if we're trying to make, you know, this prototype of our full camera from scratch, we could use Zemax to design our lenses. So the actual glass components in our lens. We would use Lumerical to design the imager, so like the camera sensor that's at the back. And then we could use Spios to bring in the full 3D environment, what the lighting conditions are, what the materials are, and if there's any moving objects in our field, you know, is our shutter speed fast enough to capture that. Next slide, please. So kind of walking through what the design workflow would look like if, like, you know, if I wanted to design a camera from start to finish, what would those steps look like? So we'd first start in Zemax. So actually all of the images you see on the right are from Zemax. So the one on the left is the cross-section of a cell phone camera lens, actually. So off of the left, it's like the scene that you're imaging, and there's a cover glass, and then all of our optical glasses, and then we have an infrared filter at the back before it hits the camera sensor. And then those two images on the right are just like different imaging performance metrics that we have available within Optics Studio. So if I'm designing, you know, this camera from scratch, usually you don't start with just a blank slate. You have Zemax ships with a whole catalog of design templates, so you could find, you know, something similar to what you're ultimately going for, and just make a few tweaks, make a few optimizations, and get to a better solution faster. Has a whole catalog of different materials for those lenses, allows you to optimize on what those lenses are, or what those materials are, as well as like the surface profile, the shapes of those lenses. We also have the ability to optimize for manufacturability. So, I mean, in this image, you can see there's some wonky looking lens shapes. We want to make sure that these are actually manufacturable, basically controlling the shape factor that is available to the optimizer. And I believe all Ansys tools are able to be automated via API, definitely Python across all of them. Next slide, please. So once we have an initial design that we're happy with, we can go into tolerancing. So this is where we introduce real-world manufacturing and assembly defects to determine how it's actually going to operate in the real world. So we can design like a perfect lens that looks amazing, but if it's just one lens is made just slightly wrong, how much is that going to impact our performance? So we can do tolerancing and then count for both fabrication and assembly error, so like the actual making of it and like putting all the pieces together. We can look at tolerances both optical and mechanical, so both the lenses themselves and how they get mounted into the system. And then there's different type of tolerancing. You can look at sensitivity analyses, which is basically how sensitive is each component to like how much of an overall impact on the system is it to have like that one lens made correctly. And then Monte Carlo gives you an idea of like overall yield of, you know, combine all the different tolerances together. How good do we expect this lens to actually be when it gets made? Next slide, please. So a bit on the multi-physics piece. So if we have our lens, we're happy with it, we've done our tolerancing, we want to see how it's going to perform under actual real world conditions. So like say, for example, I'm designing a camera, but it's going to go like operate on a satellite. And so those conditions are different than, like here on Earth. Maybe the temperature is different. Maybe there's different, forces as the satellite's being launched into space. Do my lenses shift around? Are they still going to perform? Actually, the Hubble had a problem with that, where the mirrors didn't get, they didn't properly do structural thermal analysis, and once it was up there, they ended up being out of focus. So it's a very critical part to your optical system design. But basically, the way it's done, so once you have a design, your optical design and like the mechanics that are holding it, we can send it to a FEA tool to determine what the different structural and thermal loads will be. So like if there's a temperature gradient across our lenses, like the stress on how each lens is being held, as well as like just general gravity and forces under operation. And so all of those are going to have impacts on the lenses, like the shape of the lens itself, as well as like the material density, so the refractive index. And it may not be uniform across all. So this is why we do this type of analysis. And that information can then be brought back into Optics Studio, where we then see what the performance is going to be, after all of these deformations have happened. Next slide, please. Next slide. So once we're happy with our camera system, we can export it to SPIOS. So ZMAX is really good at its ray tracing. It's really good at image generation. So why not let it handle the lenses part of the system, where we can use SPIOS to build up the full 3D system. So basically, this is just the capability of the way the two talk to each other, where ZMAX pre-simulates the important optical components like distortion, vignetting, resolution, and focus, and then passes that off to SPIOS. That's like the way that we can bring it in into SPIOS. Next slide. So once our lenses are all good and imported into SPIOS, we can import our CAD model. So we build up our full, 3D environment that that our system is operating in. We apply the different material properties to the different objects within our scene. We apply whatever lighting conditions are going on, and then we can start running some simulations. So some ideas of different simulation results that we can get. Most simple, quickest is a pixel grid projection. So for example, if we're trying to do like facial recognition, we need to have a certain number of pixels across someone's face in order to be able to resolve it. So we can do a quick check of whether we're going to have enough pixels like to theoretically even resolve it, depending on like the magnification field of view of our camera. A little bit more complex, we have geometric simulations. So basically just a check of what the field of view of our system is, like good if you're trying to determine where you're placing this camera, or if like the field of view of it is sufficient. And then photometric simulations incorporates in all of the material and lighting information into the simulation, so we can get a picture of what the scene is actually going to look like. Next slide. So in parallel, we can be doing an imager development in numerical. So we're designing, the sensor, the camera sensor at the back. So we can, in numerical, design micro lenses, which help us focus more light onto our sensor. Color filters, so different pixels are sensitive to different colors. And then our metallization and silicon substrate are what converts our photons into electrons. So we can do both the design and analysis part within numerical of these different components. And ultimately, for this type of work, the key result that we're looking at is our quantum efficiency, which is basically the ratio of how many photons that hit our sensor end up getting converted to electrons, because that's actually what's being read. And that's on a pixel by pixel as well as like wavelength basis. So that's the information that we want from numerical after we finish our design. Next slide. And then, so bringing it all together, so, in SPIOS, we run our simulation, we have this resulting exposure map, which is basically just a map of the the photons across the screen, how many photons we're hitting each pixel. We have our SPIO sensor system exporter, which is how we apply the numerical information, basically converting those photons in our exposure map into what the electrons will be, which is then turns it into the raw image you see on the right. So we go from photons to electrons for our raw image. And then we can even add in post-processing algorithms. So most commercial cameras have some level of post-processing algorithm built into it. If you have details on what that is for your camera, or maybe you're playing around with what it should be, you can play around with that in SPIOS and determine, exactly what your final image is going to look like. And yeah, that's how all of the different components play well together. And I think that's it for me. I'll pass it on to Ben.
Real quick, Ben, before you go,
Sure.
sadly, our marketing contact, Gabby, has lost audio. So instead of saying next slide, we want to just give her a nice little thumbs up when you're ready to move to the next one.
Okay.
Thank you.
Gabby, can you see? Okay,
There we go.
thanks.
All right. We're testing out the new method. Thank you.
Okay, so technically, the structural or any thermal simulations all come under the flagship of something called Ansys Mechanical. And Ansys has a plethora of simulation tools in mechanical. If you broadly, here are some features, like you can run a static structural to a transient simulation, can involve nonlinear materials. I'll be talking about some of these slides shortly. It also has a very interesting and user interface. It's a very good, very friendly user interface. And then you can also do some topology optimization to optimize geometries, meet certain objectives. But the biggest asset of Ansys is, this multi-physics communications. Multi-physics, two projects, two of different fields. We can, share information and solve in the same project space. Next slide, please. Thank you. So, as I said, it's a friendly GUI workbench. If you really look at that, the schematic C and D, they are two different projects. One is a static structure, one is a kind of explicit dynamics. Now, both are, obtaining information from an engineering data, and there's a common geometry. So these kind of workflows is made possible through this GUI option. So you can, run any type of analysis and start passing information. And so that is the greatest advantage of Ansys Workbench. Next slide. As I said, one of the biggest assets or the beauty of Ansys is actually multi-physics coupling. What you see on the screen is, a CFD analyst could have done, using CFX or Fluent, some CFD analysis, and then a structural engineer like me could run both steady state thermal analysis by mapping some of the temperatures that come from the fluid analysis, or even mapping the pressures from the static to the static structure analysis. On the other hand, the one can also do a two-way between the CFD analysis and static structural. So a good example would be, it's like a two-stroke engine where there's a reed valve. The reed valve vibrates and it alters the flow of the pressure in the combustion chamber. At the same time, it also alters a change in pressure can alter the vibration of the reed valve. So if you want to study something like that, Ansys has this multi-physics coupling, and you can see again it's done in one place in a GUI form. Next slide, please. Thanks. One of the things that is if you run any simulation, pretty much in the mechanical domain. You pretty much go and say, okay, what's the material? What are the geometry? What kind of, obviously have to mesh. You're running an FE analysis simulation, and you're looking at results, post results, getting into writing reports, or even, exporting to an Excel file and doing some post calculations. So it's usually this is the routine. And so that is easily done. Um, Next slide, please. Yeah, that's easily done. So when you get into Ansys Mechanical, what you see on the screen is if it's not clear, but it's a kind of a modal analysis, a vibration analysis is done, and a static structure analysis is done. But the entire schematic, what was mentioned in the previous slides, are all introduced here, or you're done in a GUI form. And recently, I mean, it's going like an iPhone type, where you can even insert some apps, maybe certain, fatigue calculations or certain critical speed analysis, or even certain turbo machinery, force mappings. So these kind of ease is introduced within Ansys Mechanical. Next slide, please. Now, obviously, when someone says you're doing a static structural, one biggest thing would be strength, right? You want to test the different assemblies or structures for different load conditions and find out what the stresses on deformation. So if you go look at the top right, it's the most complicated one. It's a boot made up of hyperelastic material, probably pressurized, and there's a self-contact. And so all this is kind of accounted in the part of strength analysis. On the bottom left, you can see if one wants to look at the plastic deformation, right? So how can you analyze that? And that can also be done. Or any kind of a transmission system or a blower or anything like that, we can analyze it too. Next slide, please. I'm going to the dynamic side. Dynamic side, you can do a lot kind of, you can do a modal analysis, a harmonic type of vibration, even random vibration. Here is an example. What I'm showing on the screen is shock spectrum. So it's very common, particularly in aerospace industry. They run something called, they'll give a shock spectrum and they'll ask you to do a shock spectrum analysis, or often commonly known as response spectrum analysis. So here you can think of like a bridge that is subjected to some kind of a wind loading, and then you want to see, what happens to the responses. So obviously responses are vibration responses, but finally you're looking at stresses and fatigue and so on and so forth. Now, when you are involved in static structure analysis, you're always you are asked to kind of optimize your design based on like minimum mass, increased stiffness, low stresses. At the same time, it should be able to manufacture it. And so that's where we can also do something called topology optimization. So again, if you look at the project schematic, there is a gray portion of it, which is pretty much common between static structure and topology optimization. And then data is transferring through a link. And the C portion of it is once you do the topology optimization, you kind of want to validate it and see if it really makes sense. And so that's the schematic C. So whatever you see on the screen is pretty much displayed or can be done or simulated with just these three project schematics. Next slide, please. Now, LS Dyna, it's a very famously, it's all like the #1 software for any kind of explicit analysis. And Ansys has bought it, and LS Dyna is a part of Ansys. So you can do like crash testing or impact or even some kind of like, if you have a container that's you're transporting and you want to see if the parts of the container are flying off, or so on and so forth. So it comes under Ansys LS Steiner. That's one of the softwares also available. Next slide. Final slide is if you go to any automobile industry, they're into a lot of Six Sigma and sensitivity analysis, and Ansys is like recently developed a very interesting multi-purpose tool to do a lot of sensitivity analysis, and not only in design parameters, but also maybe in cost, weight, some even corrosion resistance and so on and so forth. So this is not just exclusively to mechanical, it's also extends to HFSS and Maxwell. And so the thing aspect of it is that almost most of the applications that we talk here do have a handshake as a multi-physics application. And that is it, I think. Next slide.
Awesome. Thank you, Ben. All right, I'm going to do this in about 60-ish seconds to make it quick, and we can get to the questions, because I know there was at least one that popped in here. And obviously, if there's any other questions you do have, feel free to shoot them out. That's not the Gabby thumbs up system. I love it. Okay, so real quick on the eligibility criteria, a few things that just will allow you to qualify for the Ansys Startup Program. Have to be a privately held company, less than 10 years old as a company, have less than 5 million in annual revenue. This is a bit in flux. I think it might actually be closer to 10, but roughly around that amount. And you cannot also be an engineering consulting firm or simulation services company. Other than that, I mean, this, I'll get a little bit here on the next slide, but if anyone has interest, at least just in the products themselves, I mean, the good thing is that, our engineering team, it would be available to kind of discuss your particular use case, because obviously there's a lot of different questions and discovery that happens on both sides for that. But just a couple quick stats on the startups. We have over 1,400 startups in 50 different countries. One that is actually near and dear to my heart is the one all the way to the left right there, which is Junyali and her team over at Photonect, which is based out of Rochester. We've met with them a ton of times. They're great people to work with. They come out of NextCore, one of the incubators based in Rochester. Her and Dan are great. So, I mean, if it's, right there and within the rest of our company space for startups, it really is, getting you the tools, access to things that you normally at that stage of your startup are not going to be able to afford. I'll just lean right into the last one here, Gabby. These are the bundles. So I'm not going to even come close to going through all of these, but the main three that we focus on, at least at SimuTech, are electromagnetics bundles, the structure and fluids bundle, which would be the FEA and CFD, or the optics and photonics. You don't have to limit yourself to one. You just can't take, it's not a la carte kind of thing. You can't take some from one and put it into another bundle. What I would say, any kind of estimated value to put kind of a dollar figure on how much all of those licensing are worth. Each bundle is in the close to hundreds of thousands. Maybe the structures and fluids comes pretty close to $1 million worth of software that we get you at a much, much smaller price. I'll put it this way, just on the pricing side of things, that is truly based off of your company's revenue. A few other factors into it, obviously the age of the company, any kind of insight to the application, which if anyone is interested, obviously we can get you a copy of. But Ansys will kind of work with understanding that if you're either pre-revenue or funds are very limited, these are the tools that will be able to get you to solve the problems that you need to solve to get to the next stage in your process. If there's anything to take away from, obviously all of what we had done, and I'm sure anyone on here, and there's a couple of questions we can get to, of course. If you have an engineering problem, there's more than likely a solution with one of these products at Ansys. I think that's it for my slides.
Awesome. Well, we definitely had a question.
Yeah, I think we're good for that. You can, if you want to go ahead and throw it out there.
hang on, where did it go?
I already replied to that.
Ben, yeah, Ben took
You
a
did.
shot at it. So thank you, Ben. And then there was, I think, one more question. If you've not formed an entity yet, would you still be eligible for the startup program? Sort of where in, where do they need to be in their lifespan, in their life? So our early stage program, which we're currently wrapping now, they actually don't need to be an entity, but to get into our next program, they will. But how do you look at that?
Yes. So, I mean, I'm assuming it would have to be some type of entity. I don't put it out there. A lot of times you'll have to have, an actual, don't necessarily have to have a website per se, but you will have to have some type of domain for your email access. You can't really use, Gmail or any of like at Cornell or edu types of address. You do have to have some type of domain. So that would obviously follow up that you should be an entity to be able to take advantage of it. But good
Okay.
question.
And if they're interested, they should contact you, Jordan.
Yes, I would say you can either contact right there, info@simutechgroup.com. That should go directly to our marketing team. So Gabby would be able to. Again, I support the Northeast part of North America. So kind of like that New York State,
Okay.
New Jersey, Pennsylvania, Ohio area. If at all you don't get a response back, obviously feel free to reach out to me. But I would say info@simutechgroup.com is going to get you to the right person in the right place.
Okay. And
For those outside of New York.
yeah, you mentioned an important point because our other programs which are more virtual. We have people from across the country, so many of them are not in New York. Obviously, they're all over the
Yep.
place. Okay, that would be the standard place to start. Okay.
Yeah.
We're losing people quickly if there's any other questions, but otherwise, hoping to see Jordan, if not others from his team, down at Demo Day a week tomorrow. Thank you for taking the time today to talk about your products. There were a couple things that I think it's interesting. Everything we do in our early stage program, not everything, but many things we do are in the same category. Like make sure you're building a business that solves a problem that people want to solve. And I think the parallels of make sure what you make actually, does what you want it to do.
Mhm.
Do those things as cheaply as possible because making stuff is expensive. So if you can simulate it, all the better. So I think it very much dovetails with our view of entrepreneurship and, figuring out everything as cheaply as you can before you make a pile of stuff that doesn't quite do it. So thank you for taking the time to be with us today.
Absolutely. No, thank you for having us, Ken. And to my coworkers, colleagues over here, I appreciate you guys taking your time out to go through all of this. I will definitely be down at Demo Day next week. So if anyone else will be there who's still listening here, feel free to come up, say hi, tell me your story, and we'll have a conversation from there. Thank you guys so much.
All right. Well, thanks for your time, everybody.
Thank
And
you.
thank you. Thank you, everybody.
Bye.
All right.
All right.